Uh, okay, cool. Well, I guess we should probably get started. Yeah, so I actually saw Diganta presenting about this topic at a workshop at Mila that Arena was hosting that I was attending, and it was something I hadn't really seen before, and I thought it was very interesting. And I think part of this meeting is about kind of discussing new topics that are a little bit outside the box of what we've been thinking about so far. So I wanted to invite Diganta to talk about this at IBM. Um, and so, yeah, whenever you're ready, you could take it away.
Perfect. Yeah, thank you so much for inviting me, Matt. It's very refreshing to talk about these ideas. Just a TLDR that most of the ideas or works I'll present is also by IBM, by Pinyu Shen. So before I start, again, I have tried to um, keep this presentation aligned with the general agenda, which, as written in the title, is Modality, Agnostic, Adaptation in Deep Learning. But there are specific bits and pieces which might stray away from adaptation, but they'll be aligned with the core topic of this talk, which is reprogramming. Okay. All right. Just a high-level overview. What we'll be discussing today is we'll briefly go over standard transfer learning settings, fine-tuning, linear probing, and a few other bits and pieces that have come up recently regarding large-scale transformers. Um, and then we'll go into the core topic of this talk, which is reprogramming. I'll start with giving high-level overview of existing works on reprogramming before going into a bit of theory and overview, and also where to identify failure cases. And then I'll discuss mostly about the ideas that me and my colleagues have been working on with some preliminary results. I highly invite the audience to engage in discussion on these ideas because these are ideas which are in preliminary discussion. So any feedback, criticism, or advisory regarding what can be done better to align these ideas with the general goal would be really helpful for us. Okay, with that, let's start. So over the years, we have been seeing a lot of models being trained with larger and larger parametric capacity. And this is aligned with recent advances in research on model scaling. And these models, which are of exceeding capacity, have demonstrated strong performance in downstream tasks, especially when you see models in the domain of language. We have been seeing starting from BERT. Now we are up until nearly 500 billion and more parameters, which is huge. But the paradigm of these models are promoted in a way that these models not only exceed other models in the tasks that they were originally trained on, but also subsequently on many other diverse set of downstream tasks when they are transferred to the same setting. So with that kept in mind, let's at least first understand what transfer learning is, why should we care about it, and why it is an important area in deep learning research. The first thing is the context of transfer learning applies to where you have a pre-trained model that you have trained on some existing diverse data set. And the model now has a sufficient representation capacity that it can be used subsequently on a downstream task of the user's choice. So uh, for instance, take into account a ResNet 50, which was a standard vision model, which is trained on ImageNet. It can be further used as an encoder in object detection model like a faster RCNN or a mask RCNN with minimal to no fine tuning. So you can just freeze it and add a decoder and do your object detection, right? So one of the very preliminary types of transfer learning was fine tuning, where you take a pre-trained model and then you update most, if not all, of the weights by training it for a few iterations on a subsequent downstream task. This usually results in the best results that you can obtain on the subsequent downstream task, because you view the pre-trained model weights to be a standard good initialization for the subsequent downstream task that you want to train on. However, this comes at a very high computational cost, because retraining all the weights or fine-tuning all the weights on a downstream task, depending on how complex the downstream task is, can be really expensive. But there have been papers that have tried to mitigate this by identifying which specific parts of the model you should fine-tune, or trying to innovate the process of fine-tuning by making it much cheaper than full fine-tuning, as highlighted in the references. But in this general paradigm of fine-tuning, one of the two most important domains is the pre-training regime. So how well the model that you're fine-tuning has been pre-trained. It has a significant importance in the downstream task performance. And also, most fine-tuning experiments or papers that do full end-to-end fine-tuning are modality constraints. So you usually have a pre-trained model on the domain of image, and then you fine-tune it on a downstream task, which is also on the modality of image. So it's not usually obvious how you can take an image-based model and just subsequently end-to-end fine-tune it on a language task, for instance, without making substantial changes in the model. If you flip the coin, so I usually say transfer learning is a coin with two sides. One of them is fine-tuning and the other is linear probing. There is a elegant trade-off that comes into play when you compare linear probing with fine-tuning. Usually in linear probe, you usually just replace the head of the model, like the classifier head or whatever the task-specific head that you require for your downstream task, and you only tune the parameters of the new head and keep the main feature extractor or the representation learner or the backbone frozen, right? So if you view it against end-to-end fine-tuning, then this is rather much more computationally inexpensive. But if you compare it against fine-tuning, the results are not as good as you might get with fine-tuning, which is in obvious nature. So, and usually in linear probing, we see most of these papers that do linear probing are relying on pre-trained feature extractors, which have been trained with the self-supervised objectives. So take a ResNet 50 with just the feature extractor part of it, and you train it using a self-supervised objective like SimClear, and then you want to adapt it to a downstream task, for instance, CFAR, then you'll attach a CFAR specific classifier head that you will only tune during the downstream linear probing. However, there have been certain papers that have tried to switch the narrative between trying to adapt models to subsequent downstream tasks without requiring A, full end-to-end fine-tuning, or B, linear probing. One of the probably foundational paper on this domain is transformers are universal compute engines. Here, the authors state that they do not fine-tune in a transformer the self-attention or the feed-forward layers in the residual block. They call it as a frozen pre-trained transformer. They only fine-tune the affine parameters that they have in the normalization layer. And they say that if you do this minimal tuning, then you can use a transformer on subsequent many diverse downstream tasks in different modalities, and it will be very, very efficient. And they also highlight that how pre-training on natural language as a modality is very dominant in for transferring to the model to subsequent different modalities. They try it on a variety of tasks, and I highly encourage people to take a look at this paper. But this is one of the papers that tried to address the flip coin of fine-tuning against linear probing. And there is another paper that also tries to somewhat do this at a very high level called as unit. Um, they try to do this by having a unified transformer where they just switch the head of the model with like a task specific head and use a frozen pre-trained transformer to do diverse set of tasks. Like you can do object detection on images, you can do visual question answering, and other tasks using a single unified transformer. So we are seeing a general trend that people are more shifting towards how we can use pre-trained models without having to utilize a lot of compute to transfer them to a downstream task. Uh, okay, given that pretext of what has been the standard research in adaptation of deep neural networks in subsequent target tasks, uh, I wanted to introduce this concept that would be the core area of this talk, which is called adversarial reprogramming. This was first introduced by Elzayed et al. And Goodfellow in 2018, which was subsequently published, I believe, at ICLR 2019, where they tried to address this concept, where they state that if you have a pre-trained model that you have trained sufficiently well on a source task, and the notion of sufficiently well comes from the fact that you measure it using some metric that is defined on the source task, then you can just reutilize the model as it is without changing any of its weights onto a downstream task by solving one simple optimization problem, which is to map the data manifold of the downstream target task onto the data manifold of the source task on which the model was originally pre-trained on. So in this setting, I would highlight the example that the paper proposed. Assume that you have a ImageNet pre-trained model, which does perform sufficiently well on ImageNet. Assume it is ResNet 50, for instance, and the image dimension of ImageNet is 224 by 224. And now, let's say you want to reprogram this model to solve CFAR 10 task, for instance, or MNIST task, for instance. Now, the image dimensionality of MNIST image is like 16 by 16. So what they suggested to do is take the MNIST example, which is 16 by 16, and place it at the center of a pixel grid, which is the size of 224 by 224. Now, the frame that you're left with is what they will learn a white noise for. So you can see the white noise that they're learning here is delta, and they have a mask that they basically take the target image, which is MNIST, and put it at the center of this pixel grid, surrounded by the white noise that they learned for. And now you will obtain a 224 by 224 resultant image at the center of which is the target image coming from the downstream task on which you want to subsequently transfer the model to. And if you pass this image directly to the pre-trained model, which was trained originally on ImageNet, and do hard-coded label mapping at the end, where you just label remap from ImageNet label 0 to MNIST label 0, for instance, then you will be able to solve MNIST using ImageNet without zero parameter change in the model. So you're not changing any parameters, updating any parameters in the model along with its head as well, because you're doing a hard-coded label map. So I find this idea very elegant and interesting because think of it in this way. If a model has strong capacity of building representation, which is linearly separable on the source task, then if we map our target data on which we want to transfer a model to, if we map that data manifold to the source data manifold, then the model should be able to also separate that target data manifold as efficiently as it can on the source data on which it was originally trained on. So that is the original motivation of adversarial reprogramming in general. However, there are a variety of flavors that have been subsequently proposed after this work. And the first one that I want to highlight, which I find very important, is the ability of reprogramming not being limited to modality. So in this paper by Nikara et al., they are able to reprogram a pre-trained vision model, which is a convolutional model, uh, to do sentiment classification on natural language. So they have no language specific head or language specific layers in the image model that they have originally trained on, but they're still able to transfer it from a different modality to another modality. And the way they do it is, as shown in the figure in the slide, they have a sequence of token which represents a sentence for which you want to classify the sentiment of. And for every token, you pass it through this embedding lookup parameterized function, and you generate a visual patch. And then you stack these visual patches together, and then you just mix it up or overlay it with a base image that they call XC. And the resultant image that you get, F prime theta t, is your reprogrammed input. If you pass this reprogrammed input to your victim image classifier, which is fully end-to-end frozen, then first you will get the labels to be from the original label space of the pre-training task on which it was originally trained on, and then just simply do a label remapping, and you should be able to get the sentiment prediction on this sentence from a fully convolutional model. So remember when I was discussing earlier about fine-tuning and transfer learning in general, they were all seemingly constrained by the fact that the pre-training and the downstream modality were the same. But here you are no longer bounded by that constraint. So you can take a language model to solve vision tasks, a vision model to solve language tasks, and so on and so forth. So I find this paper to be one of the highlighted papers that try to address this. Also, another really interesting paper, which was proposed by Yang et al., in which Pinyu Shen was also an author at ICML 2021, where they tried to reprogram a pre-trained acoustic model to time series classification. I won't specifically go into the way they are able to do it, which is demonstrated in the diagram. But one thing interesting that this paper highlighted is why it can be so beneficial to do reprogramming as compared to end-to-end fine-tuning. So as you can see, if you take the model that they had, the pre-trained acoustic model, onto the target data set, which is to classify between these two classes of adulterated strawberry against strawberry. If you see the TSNE plot, the feature distribution before reprogramming or before basically transferring, the features don't look separable. And after doing full end-to-end fine-tuning, the features still do not appear to be separable. But if you do the reprogramming method that they proposed, which they call V2S or voice to series, you can see there's a nice separable hyperplane between the features of the two classes. So in fact, if you look at the results of this paper, it not only beats the full end-to-end fine-tuning benchmark on 30 data sets by a large margin, but it also outperforms the state-of-the-art model that was trained from scratch on the target data set. So I find that to be quite remarkable, because basically reprogramming is utilizing the power that is held in the pre-training of a model. So if you have a better and better pre-trained model and you reprogram it on subsequent downstream tasks, you should be able to see better benefits as compared to if you just trained it from scratch on the target downstream task itself. Because you can assume that in many cases, the target downstream task might be sparse in nature or won't have enough data adequacy to fully learn a full model. So it's better to rather utilize a pre-trained model which has been trained on a diverse set of data. Now, I would say that reprogramming is, as a concept, might not be very, very new. It can be attributed to different jargons. One of them is called visual prompting. In this paper, they do prompting on a clip, frozen clip architecture by OpenAI, and they use very similar concept to that of reprogramming, but rather they call it as visual prompting. And the only difference that happens in this framework, as you can see from this figure, is that in conventional reprogramming, we just add this visual prompt or the reprogrammed frame on the image and pass it through image encoder, and then we do a hard-coded label mapping. But in their paper, they additionally utilize the text encoder of clip by providing an additional text prompt. So all they're trying to modify is the label mapping aspect of reprogramming, because the visual prompt of the reprogrammer still remains the same as it is in standard reprogramming. And if you dig up literature, then you'll find a lot of papers call this end-to-end process as visual prompting or in general prompting, but the idea behind it still remains the same as that of reprogramming. So and also if you look much farther back, then you might see literature where you do projection matrices for doing subspace clustering, where you might take different data samples that you obtain from different distribution, and then you use projection matrices to project it to a common subspace on which you do subsequent clustering. So you can view all of these methods to be under the same regime that we call reprogramming. And just another paper to highlight, because I've been talking so far about how to adapt models from one domain or one pre-training task to a subsequent downstream task. That's not the only premise of reprogramming in its capabilities. People have used reprogramming for open set semi-supervised learning, as this paper suggests, although again, they brand it as visual prompting. But the overall idea, as you can see from this figure, is still very relevant to the original motivation behind reprogramming. I won't go into the specificities of these methods because they're very fine-grained in nature, but I just want to highlight with these slides that the overall framework that these papers are utilizing is very much the same framework as that of the original reprogramming paper. There are some theoretical implications behind reprogramming, and there is this paper by Englert and Lazick. They prove that you can actually reprogram a randomly initialized two-layer ReLU network on Bernoulli data models as long as the network width is no greater than its input dimension. They also showcase a failure case, which is that if you take a two-layer ReLU network on orthogonally separable data sets, then it can cause their adversarial reprogramming to fail. And they also suggest a strong baseline on where to guarantee reprogramming would work, or they call it as susceptible to reprogramming, because a model can be reprogrammed as long as you have the batch normalization layers to be suitably initialized. Now, this paper is quite long. There are many comments that the authors make regarding what are the capabilities of reprogramming and where it fails. However, the fact that they try to prove that you do not essentially need pre-trained model and you can reprogram a randomly initialized network is quite interesting. However, take it with a grain of salt, because in practice we haven't seen that really happening so far. But it would be really exciting if we do not, or if we no longer require the premise of reprogramming on full pre-trained models and just using randomly initialized networks to reprogram on a target task with non-trivial performance.
So with one question about your last slide is, like, I guess, like, this is, I think one thing that strikes me about, like, this reprogramming thing is that it's kind of like an alternative perspective on adversarial examples, where it's like when you say susceptible to reprogramming, I guess the flip side of that is that it's also that means that it's like could be extremely influenced by adversarial examples as well. Like,
Yes.
is there a difference there, or
No, not really, because that's a good point. Because the reason that they use this language, which is susceptible to adversarial reprogramming, is the fact that you can use reprogramming for good, and you can do reprogramming to turn a model into a victim model. For instance, like you can attack the model, which maybe is trained with a robustness objective, and attack the model by just reprogramming it. The only constraint in these settings is that most, if not all, the reprogramming settings are done in white box settings, which means you have access to the pre-trained model weights, right? And many adversarial attacks or robustness papers that are coming out these days are having black box assumption, which is not an assumption that we hold in reprogramming case. But you're absolutely right that we can connect this paradigm to adversarial learning in general, which is why the original paper like original paper is titled as adversarial reprogramming and not just reprogramming, because they hold a lot of commonalities between the two. If that answers your question.
yeah, yeah, definitely. Thank you. That's interesting.
Okay, so uh, I want to just highlight the overview of what reprogramming is, and when I discuss about reprogramming with a lot of people, they confuse this paradigm with domain adaptation. But I would rather beg for thought that one should view reprogramming as rather recycling or repurposing models and not necessarily a domain adaptation technique. It might hold a lot of similarities with domain adaptation in general, but the underlying goal of reprogramming is definitely substantially different than that of domain adaptation, or has much more flavor to it than domain adaptation does. Um, and just to highlight the pros is that reprogramming is generally in nature very cheap. The original reprogramming paper that I demonstrated is just adding a few thousand parameters in total to learn that frame, as compared to using the full like 50 or 100 million model to fine tune or do linear probing on. The most important pro of reprogramming that I feel is that it is agnostic to modality changes. You can take an image model and reprogram it to solve a language task, which is pretty exciting. I at Morgan Stanley with my collaborators have also been working on taking image models to reprogram it on time series. So I feel like there is a lot of importance to dig up in these settings where there is a drastic shift in modality in your downstream task. And it often provides competitive performance, if not outperforming end-to-end fine-tuning. However, it does have some drawbacks. It's not the holy grail of model adaptation in deep learning. One of the drawbacks is that it does fail when the inputs are low dimensional, and it has a very high degree of assumption right now in practice on the pre-training of the model that you're using. So whether it is a well pre-trained model or not. But although I do understand that the previous theoretical paper does demonstrate that randomly initialized neural networks can be reprogrammed, but it's just not evident as of now in practice. Now there is this paper
Excuse me.
that
It
yes.
might be interesting to compare what you're doing to some of the domain adaptation techniques. So for example, you could take the reprogramming trick, add one of the things that people often do in domain adaptation is they add a discriminator at the end. So you've got two domains, and you want to teach the model train the model so that it can't tell the difference between the two domains.
Yes.
So you build a discriminator, and then the discriminator attempts to look at towards the end of the set of layers. Can it tell whether or not it's one domain or another, and the discriminator is trained to do a good job of that, and then what's called the generator is trained not to allow it to do that. So now your generators would be the neural net plus the little piece at the beginning that's the head, different heads, and then you build a discriminator that says, can you tell which input which domain it came from with that domain's head? And then that might allow you to do a better job of domain adaptation, because you don't need the labels. You don't need as many labels for the domain. You just need a bunch of unlabeled domains. And you can train the middle section as well as the head.
Yeah, that is a very interesting point. Yeah, I really like that idea. I mean, I would say that there's definitely possible. The only thing with reprogramming is that, especially in visual domain, it sometimes does not provide as competitive performance as you would get with standard methods. But I think just like you highlighted, these are just ideas which haven't been explored in substantial amount. So we do not yet know the full capacity or the capabilities of where we can use reprogramming, including on domain adaptation tasks. So I think that's definitely possible and should be explored. So thanks for highlighting that. I'll take a note of it. But yeah, that's a really interesting point. Okay, so just to highlight on the failure detection again, there's this paper by Zhang et al. That use this metric that they call as gradient alignment. It's just the average norm of the input gradient, and they say that this metric, this gradient alignment metric, it can be maximized when the inputs are of high dimensional, and this metric correlates with the reprogramming performance, which means that when the inputs are high dimensional, the gradient alignment is higher, and substantially the reprogramming performance also is high. And they sort of showcase this empirically in the results in the paper. If you see this table over here, the scripted S is the source domain, the scripted T is the target task, the target data set, and then the model is listed. The DA is a domain alignment score that they're using. RA is the reprogramming accuracy. R0 is the gradient alignment metric, but at the start of the optimization of the reprogrammer. And RN is the same metric, but after the reprogrammer has been optimized. And you'd see that for cases where RA is high, R0 and Rn are also high, but there are cases, as you can see, where reprogramming accuracy is definitely poor. Starts out with a high R0 or gradient alignment score, but substantially degrades after finishing the optimization of the reprogrammer. So this is one case where the paper tries to highlight that reprogrammer definitely fails, and we sort of also try to experimentally prove this in our time series experiments, and we definitely do see that when gradient alignment is low in nature, we do not obtain as high reprogramming performance as we might assume. So this is just to highlight that reprogramming is not without its faults, but there's still enough research to be done to identify potential failure cases, much more than what this paper proposes. Okay, with that, I think I've given enough background into what reprogramming is as a framework and where it has been utilized, what are its potential use cases, and some failure cases detection. Now, I just want to discuss about the ideas that me and my collaborators have been exploring and working on since a couple of months now. The first idea that I want to highlight is what we call as continual reprogramming. I assume people here are aware of the foundational premise on what continual learning is. You basically want a single model that can solve or learn or model the distribution of a continuous stream of non-stationary data. So assume you want to, one of the most popular benchmarks in continual learning is like class incremental on split CFAR10. So at task 1, you are provided the data of the first and the second class of CFAR10. And at task 2, you're provided the third and the fourth, but you're expected at task 2, once the model has finished training, it should be able to classify not only the classes it saw during the current task, but also the classes that it saw during the previous task. And one of the most important problems that people try to solve in continual learning is that of catastrophe forgetting, because if you just train a model in a sequence of tasks, it's highly evident that the model usually forgets the past task that it had been trained on. So in this framework, we are focusing on one of the subcategories of continual learning, which is task incremental setup. So you have different tasks which are demonstrated here using scripted T, so T1, T2, T3, and so on. You are provided these tasks in a stream or a sequence. And what we do is we take a pre-trained foundation model, and this can be a model like, for instance, a resident 50 or a clip, which has been already pre-trained. We have its weights. And what we do is for every task, we learn a unique reprogrammer, which is demonstrated here by phi i's, so phi 1, phi 2, phi 3, and so on. And for every task also, we have a specific label mapper as lambda I. And then we keep a hash map or a library that we update the reprogrammers in it after the task has been finished training on. So, and during inference, what we do is if you are provided with the task ID, we just retrieve its corresponding reprogrammer that was trained on the task and its label mapper, and we'll be able to provide the inference label on that sample. Now, why is this really interesting, in my opinion, is that one of the standard benchmarks or baselines that people use in continual learning is that of replay, which is that we will basically utilize some examples from the past tasks in the current task. And like, for example, if you had 1,000 examples in the past task, you can take 100 examples from it and just concatenate it with the samples of the current task, so that you're providing the model with some replay buffer so it can retain the knowledge that it had accumulated from its past task. But as compared to that, in replay, we have this memory performance trade-off, which means that the more number of samples that you have in your replay buffer, the better the performance is of the model. But additionally, you also have to pay a higher memory cost, because, for example, in images, these input images are of high dimensional, and you have to store individual samples in a buffer, which can cost you memory storage at a cost of higher performance. So, but in that, as compared to that, if you use a reprogrammer, which is a unique reprogrammer for every task, and you store only the reprogrammers, which are very small in nature, you have a drastic memory storage reduction when the number of tasks in your sequence exceeds to a high amount. So as you can see from this figure, if I just use a full reprogrammer against 10% replay, I get like 6x memory reduction in just 100 tasks, which is really a big difference. And as I said, with reprogrammer, you don't have this trade-off with memory and performance, because the full reprogrammer is expected to parse over the whole sample set that you have. So you're no longer required to store individual samples in your buffer.
So the reprogrammer is told which task it's performing?
Yes, right now that's the assumption that we provide the explicit task ID. So we have a associated ID for every task, and we provide that during inference. But I'll highlight a bit later about the potential avenues of where we would not provide the task ID, and we'll have some way of inferring that task ID using neural Dirichlet processes or or routing networks, for instance. So as of right now, this framework that I demonstrated does utilize task IDs at entrance. Okay, so what are the nice aspects of this framework? It's very computationally cheap because we only learn reprogrammers, which can be very small MLP or a linear head or specific to the task that you have. You do not have any forgetting in this framework, which is the most important part that I want to highlight, because the only shared aspect or the only shared pool of weights across the whole sequence of tasks is the frozen model, which is never updated. So since there is no update to the shared parameters in the whole sequence, there is by intuition no catastrophic forgetting, which is the most important problem in continual learning. We get competitive performance as compared to standard continual learning benchmarks. And the other thing that I personally feel very attached to is that it is modality agnostic, which means you're no longer constrained to the regime or the benchmark of continual learning, where you split the data set into different tasks of different classes of the same data set. But we can now have a stream of tasks where each task is uniquely different and of different modality. For instance, the first task can be a VQA task, the second task can be image classification task, the third task can be sentiment classification, which is not yet explored in continual learning because the existing benchmarks usually just split existing data set into different subsets as tasks. And as highlighted, there is one drawback of this framework, that we do require task ID during inference, which based on our discussion with my colleagues, there are a few ideas that can be potentially explored to mitigate that issue. First is we can try to think of this whole framework as a sparse mixture of, rather than experts, reprogrammers, and have routing network to route the specific tasks data to a specific reprogrammer based on some estimation criteria. We also are exploring potential avenues of using neural Dirichlet processes for reprogrammers, where they do estimation of the non-stationarity of the data, and based on the fact that the data does not belong to a pool which can be used by an existing expert, it will keep them in a short-term memory, and they'll learn a new expert on that short-term memory. And in our case, this expert would be a new reprogrammer. And we are also thinking of utilizing model soups, or if you're more familiar with stochastic weight averaging, by taking the average of the unique reprogrammers that we learn for each task, and then have a single reprogrammer, which is just the average pool of all the reprogrammers that we learned in the whole sequence. And it has been shown in existing continual learning on speech processing papers that if you take the best model at each task and you take the average of their weights, then they should be able to solve all the tasks in the stream with a high degree of performance. So we want to reutilize that framework, but in the context of reprogrammers in our continual reprogramming paper.
Okay, can you go back to the previous chart? I have a question there. So
Yes.
indeed, your con is pretty severe, right? I mean, a new task come in, you have to know which set of parameter reprogramming to use, right? You have to know the task ID. That's something that normal continuous learning does not require. I mean, isn't that the idea? You continuously learn. So whatever in the past you have learned, if you really have a good continuous learner, you don't have to know what that task is. You just can do it, right? Because you have seen it before.
Yeah, that's a fair comment on this framework. I do, which is why I highlighted that one of its major drawback is that we require task ID as of right now. But we strongly believe that utilizing a framework which is neural Dirichlet processes, which I did not put in the slide because of its verbosity, or utilizing routing networks, we should be able to mitigate that assumption that we require a subsequent task ID during inference. So we believe that in a few months we should be having a framework that can do reprogramming in a continual stream, but have no distinction of task boundaries in a setting like this. So I don't have.
I don't know the
Yes.
idea of this Dirichlet process, but maybe can you take a look at the new task? You don't know the ID, but compared to previous data that you have experienced before, I mean, have a rough estimate what that task might be, or I mean, the new task may not even belong to any of the previously seen tasks, but it could have a nearest neighbor, right? The closest that you can think of, and the notion of closeness in the task space can be useful. I mean, have you thought about that as a way to?
Yeah, that is exactly what neural Dirichlet process is. So it does estimation of the fact that whether the data belongs to a task that was seen before, and if it does not belong to a task it has seen before based on its estimation criteria, then it will put that data sample in a short-term memory pool. And once the short-term memory pool has been filled, it will learn a new expert on that pooled data. And then it will just keep doing that in a sequence. So that is why we are exploring the neural Dirichlet process framework for mitigating the requirement of task ID. But yeah, that's the exact premise of the idea that we are exploring. Okay, another idea that we want to look at is the training objective of reprogramming. Recall that we do an end-to-end reprogramming in the case where we have the mapper which maps the data manifold of the target to the source, and at the end we do a label remapping from the like the space of the labels of the source task on which it was trained to the label space of the target task, and then we have a simple cross entropy loss against that. But in this framework, we want to look at a full SSL framework, which is a self-supervised learning reprogramming framework, where we use a frozen representation learner, F theta, and we just reprogram one modality, which is like a caption modality, for instance. Then we just use this as a standard SSL framework. So instead of in SSL, you have usually two positive views. So you augment a sample into two different views, and then you try to maximize the representation alignment between the representation of the two different views that the encoder provides. But in this case, instead of having two augmentation of the same sample, we are basically having a pair of a sample, which is a sample and its corresponding caption, for instance, and we learn a reprogrammer only on its one branch while sharing the encoder and try to maximize the representation alignment. So this is just a additional framework that we propose to learn a reprogrammer rather than requiring the whole label remapping correspondence that earlier reprogramming papers use. Another aspect that we are exploring is how we can solve visual question answering tasks using reprogramming. And in this setting, we are exploring two things. One is how we can do it using just a language model, and how we can do the same using just a vision model. And the importance of doing this is to understand which modality pre-training has higher relevance towards solving VQA. Usually in VQA task, you'll see that you have an image and a question pair, but for both of the two modalities, you have modality specific encoders, which is a vision specific encoder and a language specific encoder. But in this setting, we just for this language model one, we are just utilizing a single text encoder and reprogramming the image into the text space and utilizing a single frozen text encoder to solve VQA. So consequently, the flip side of it would be to use a single vision encoder and reprogramming the text space of the input to the vision space of the input and utilizing a frozen vision encoder to solve that task. We have some results on this on the VQA2 benchmark on MS Coco using a single BERT-based model. We haven't trained this enough, but you can see from preliminary experiments, the loss definitely does keep going down, and it does demonstrate that the idea has potential value to it. Right now, as results stand, it is actually outperforming a few of the existing literature which do utilize modality-specific encoders. So that's really promising. And the last idea that I want to highlight is to understand the capabilities of reprogramming in the context of different constraints like sparsity. So what we want to do is, if you're familiar with lottery tickets, which state that within a full model there exists a subnetwork, such that if you take the subnetwork with random initialization as the same as that of the full model and train it under the same setting from scratch to convergence, it will result in the same performance as that of the full model, if not better. So we utilize the same framework, but additionally state whether if you take a full model and try to reprogram it on a target task, and you take its correspondent lottery ticket and try to reprogram it on the same target task, whether there is any discrepancy in the resulting performance. We tried this some preliminary experiments on ImageNet to CFAR, and in this case we take a few different checkpoints, lottery ticket checkpoints of a pre-trained ResNet 50 on ImageNet at different levels of sparsity. But we do not yet concretely have any experiments to demonstrate there is anything different between reprogramming a sparse checkpoint against a full a full model with no sparsity constraint. But we do see in some of our experiments that the rate of convergence of reprogramming for a sparse checkpoint is substantially higher than the rate of convergence for the full model without any sparsity constraint on the same target task. But we are still exploring that direction. I just have a few more ideas to highlight. We also are potentially thinking how we can recalibrate neural networks using reprogramming. So if you have a poorly calibrated model, how you can do that post-training using reprogramming. There's actually a very exciting paper by Zhang et al., which was at NeurIPS 2022, where they actually take a model which is unfair in nature and they reprogram it to be fair in nature without changing any weights of the model. This is a very new work. I haven't fully gone through it, so I don't know exactly what aspects of reprogramming they're using. But they definitely rely on the overall framework of reprogramming post-training to make a network much fairer. There is also this idea that we want to potentially evaluate models using a large-scale reprogramming benchmark. So rather than just focusing on one target task, we'll have a suite of different downstream target tasks and how we can reprogram models on this benchmark and see whether there is any obvious difference between different pre-training regime or capacity of neural networks, or there is any scaling laws in the same. And additionally, as I demonstrated earlier, we want to understand whether reprogramming has any differences when applied constraints of sparsity or label noise. And finally, we want to try reprogramming the latest diffusion models out there, which would be really exciting if we can take an image generator model and reprogram it to maybe generate audio, for instance. Here are the references for this talk. I highly encourage if people are interested to go through them. I just want to highlight some of my collaborators with whom I've been working on these ideas, and I really thank them for the support. I believe some of them are here. And that's it from me. If there's any questions or comments or any further suggestions regarding the ideas or the frameworks I presented, I will highly encourage to discuss the same.
Yeah, so I guess we only have a couple of minutes left and some people are leaving, but yeah, thanks so much for the talk today. It was super interesting. I guess in terms of the next couple of weeks in this meeting, we'll be off for Thanksgiving next week, and then we'll also be off the week after that for NeurIPS, but maybe we'll have like one meeting or so before the holidays in December. And yeah, I guess, if anyone has any questions right now, they could ask them as people tune off. And if not, I could put you guys in touch with Diganta if you want to ask him some questions offline.
Thanks a lot.
Yeah, thanks. Yeah, thanks. Thank you.